Let's now turn our attention to propulsion methods. We'll start with methods which accelerate a vehicle to speeds which are a non-trivial percentage of the speed of light. Many of these ideas are technologically feasible and don't require unknown physics, even if some of the proposed energy sources used to power them are highly speculative. In fact, I'm not going to cover possible power sources here. We'll just assume that sufficient power is available. There have been thousands of suggested propulsion systems over the years, so rather than try and go through them or name them all individually, I'm just going to classify them into rough categories. I'm also not going to look at the practicalities of protecting the vehicle at such high speeds from interstellar dust or other objects as I mentioned in a previous video. I'll just look at the actual propulsion systems themselves. Let's first look at mass ejection propulsion. This works by accelerating mass out of an exhaust. The thrust from such a system is given by the formula F equals m dot VE, where m dot is the mass flow rate of exhaust gas in kilograms per second, and V subscript E is the exhaust velocity in meters per second. I'll link a simple derivation of this formula in the top right of the video for your interest. The most familiar type of this engine is a rocket, but a traditional rocket is not practical for interstellar travel because the vehicle can't carry sufficient fuel to generate enough ejection mass, and combustion can't provide a high enough exit gas velocity to achieve very high speeds. One alternative is the ion drive. This works by electromagnetically accelerating charged particles, that is ions, through the exhaust. These can reach very high speeds, which compensates for the low mass flow rate. Ion engines only produce a very small thrust, usually measured in millinewtons, but it is relentless and causes a continuous unending acceleration, and this can accelerate a craft to very high speeds in a comparatively short time. Since the acceleration is equal to the force divided by the mass of the vehicle, the final speed will be equal to the acceleration times time, and the distance travelled equal to a half AT squared, where t is time. A more powerful proposal is to generate a large-scale plasma and use this as the exhaust. There are several different approaches to this. One possibility is rather like a scaled-up version of the ion drive which we've just discussed. A propellant carried in the craft is ionized and energized through heating before being accelerated and contained and focused either electrostatically, magnetically, or electromagnetically. In order to avoid the need to carry all the propellant during the mission, some researchers have suggested scooping up material from the interstellar media, primarily hydrogen or helium, and using this as a propellant. The energy for these systems might typically be supplied from fission or fusion reactors. But why not combine the propulsion and power generation? We might be able to do this by making a plasma chamber into a fusion reactor and then venting some of the fusion products to generate thrust. The problem with this, of course, is that we have yet to make reliable fusion reactors even on Earth, so this approach lies in the future if it proves feasible at all. As an extension of this, you could of course also gather the fusion material, for example hydrogen, from the interstellar media, as shown in the previous example. In theory, fission products could also be used to propel the craft. One somewhat more surprising idea is nuclear pulse propulsion. Here, atomic bombs are used to push the spacecraft along, as shown in the diagram. The bombs are carried on the craft and ejected one at a time before being detonated. Finally, we come to the various light sail concepts, which depend on electromagnetic wave or subatomic particle momentum to exert pressure on a surface. One of these is the familiar solar sail concept, where a large area of thin material is spread out and pushed along by the pressure of photons from the sun or another star hitting it. The momentum of each photon is equal to the energy of a photon divided by the speed of light, and since the energy is hf, where h is Planck's constant and f is frequency, so the momentum is equal to hf over c. The force generated by this momentum is the rate of change of momentum with time, dp by dt, and so it depends on the flux of the incoming photons. The acceleration is the rate of change of df divided by c with respect to time. Rather like the ion engine, although the generated forces might be relatively small, the relentless nature of the effect means that high velocities can actually build up relatively quickly. Another idea related to the solar sail is to use a beamed electromagnetic wave, generated for example from a laser, to generate the required radiation. The photon rocket is the opposite effect, generating a large EM radiation burst in the vehicle and using the resulting photon momentum to generate thrust.